Today, our speaker is Professor Andrey Pilipenko with a talk boundary approximation for sticky jump reflected process on the half line. Please, Andrey.
Thank you. So this talk is based on my recent result with Andrey Sarantsev from University of Nevada. And at first, let us consider the following problem from queuing theory. Assume that you have a queuing system and sometimes requests arrive and depart, and it satisfies so-called linear recursion. So theta n is arrival minus departure, and we have some picture. Sometimes a lot of requests may depart or a lot of requests may arrive. And if this sum is negative, for example, xn minus 1 plus theta n is negative, so you may process, for example, more requests than you have. Then you have just 0 requests in a system. So if this variable is 0, then xn is just 0. And now assume that, for example, theta n are independent identical distributed random variable with 0 mean 0 with variance 1. Let us consider this random walk. And it's well known that by Donsker's theorem that the limit of this scaling is a Brownian motion. And the problem is, what is the limit of this sequence of processes, And the first question is it possible to have a nice formula such that this sequence X or this process is some function of this random walk? And if this function is continuous in the functional space of, say, Cadillac functions, then if you have this convergence, then you will have this convergence to gamma of W by the continuous map theorem. And the answer is yes, there is a nice map, so-called Skorokhod map. And if you have this model, then it is not a problem to get a limit for Donsker scaling. Well, if S theta attracts to, say, if they belong to domain of attraction of alpha stable law, then by continuous map theorem, you'll get convergence of, well, another scaling to Skorokhod map of alpha stable law. And today I would like to discuss problems of queuing theory that may arise when you have not a limit, not a limitless recursion, but maybe some general case. And I would like to prove and introduce some map on a space of Cadillac function, and then many processes from many. Then I will get a lot of results on storage processes or on perturbed random walks, and so on and so forth, as an application of continuous time theorem. And now just let us discuss. Now time between jumps is 1. So next generalization assumes that these times are IID, say. If you take exponential distributions, then you get continuous time Markov chain, but they may be they may not have exponential distribution. When you hit 0, this random variables may be different, and it's natural to suggest that this time may be different, because the device that processes requests have idle time, and sometimes when there are no requests, it's just turned off, and then when a new request arrives, then you have to turn it on, and you have some warm-up time. Another generalization is the following. It is possible that the jump from 0 has different distribution from jumps here. For example, if you have some plant or factory, and you produce, say, sweets, and you have a new order, then you don't have to start processing immediately. Sometimes people wait a lot of orders because it's expensive to turn on the line to produce very few items, say very few sweets or pills for medicine, and so on and so forth. And now I will recall you just definition of classical Skorokhod map, and then we will discuss, after this, we will discuss other possibilities, other type of exits from 0. And then I will formulate deterministic theorem, deterministic limit theorem, and I will introduce deterministic map. And then I will show you examples of applications to a lot of models, and then I will prove the result. Okay, now let us start with Skorochod's approach to reflection. The Skorokhod idea was the following. Assume that you have a continuous, Skorokhod considered a continuous function, but we may discuss it for any. So deterministic continuous function, and I will call this function just noise. And assume that there is a reflecting screen at 0, say the wall. And this is a movement of a robot, and when robot hits the wall, it's stuck. So when robot is here, it tries to go down, but the wall say, no, you have to stay near the wall, so it stuck. And then robot wants to go up and goes up, and then it goes down like this function until it hit 0 again, and then the program say go down, but it cannot, and the robot reflects, and so on and so forth. So what is a position? What is the position of a robot if the program is W? It may be considered like a sum program plus reflection. So you may say that program say goes down, and the wall just pushes to the opposite direction such that it compensates movement of robot down. And this process L is continuous, and it may increase only when the process X is at 0. So effect of, yes? So the effect of the wall disappears when the process X is above 0. So the wall affects only when the process X is at 0, and it appears that there is a unique solution to this deterministic problem. And there is a nice formula that X is W plus L, where L is just a running minimum of W. And I will denote this Skorokhod map by gamma. It may be seen that this map is continuous map on the space of continuous functions, and it is also continuous if W is Cadillac function. Moreover, similar problem can be formulated for Cadillac noise W, and you also have existence and uniqueness. Okay, the next slide is just illustration. So blue line is W, and green line is X. So green line is X of t. So if you are above 0, then increments of green line and blue line are similar. Now, blue line goes down and the wall pushes up, and L compensates W. So the process stays at 0, and now the process, the increments are 0. So you just go up, and you stay at 0. Then blue line goes up, and you have this picture, and so on and so forth. And now let us discuss. Now let us recall Lindley model. So from continuity of a Skorokhod map, you have convergence of scaling of X to reflected Brownian motion. And now I would like to discuss other possibilities to exit from 0. And now let us discuss diffusions, just diffusions or Brownian motion or a strong Markov process with phase space 0 infinity, so non-negative Markov process that behaves like a Brownian motion up to hitting 0. And then you may exit from 0, maybe by a jump or somehow. But and again, when you exit from 0, this process moves like a Brownian motion. And the question is, what is the generator of X? Well, it's well known that the generator of a Brownian motion is 1/2 times second derivative. Well, we have to discuss carefully the domain. And it appears that the domain of X is not twice continuously differentiable function that are bounded and have two bounded derivatives. But it is important that this function must satisfy the following boundary conditions. This result about boundary conditions was obtained by Feller and Wenzel. And let me interpret this P1, P2, P3, and the measure P4. P1, P2, and P3 are non-negative numbers, and P4 is a measure, maybe infinite, but such that integral from 0 to infinity 1 minimum x p for dx is finite. And if P1 and P2 and P3 are 0, then P4 must be infinite measure. So interpretation of these numbers and measure is the following. This P1 is responsible for killing at 0. So when process hits, it may be killed with some intensity. I will discuss a little bit later what does it mean kills with or reflects with. So what does intensity mean? But if so, this means that it jumps to symmetry, to infinity, and stay there forever. Today I will consider only conservative processes, so P1 will be 0. This term and term P2 means Skorokhod type reflection. Well, in some sense, we will discuss it later. Skorochod's reflection. So if you don't have this, and if you don't have this, then you have just reflected Skorokhod, reflected Brownian motion. So this term and P3 means like delay at 0. So 0 is a sticky point if P3 is positive. So delay at 0. And P4 is responsible for jump exit from 0. Jump exit from 0. And if P4 is finite measure, and if P3 is 0, then the process behaves like this. You have reflected Brownian motion, but sometimes you have jump exit, and P4 over the total variation of P4 is distribution of jump exit. Then you have reflection again, and then jump exit, and so on and so forth. Well,
excuse me,
yes.
Can I ask you, what is the choice of these coefficients, which is corresponding purely reflected Brownian motion?
Purely reflected is derivative is 0, and all other coefficients are 0.
So P2 must be equal 1, yeah, in this or...
Well, P2 is positive, yes. Yeah. Yes, P2 is 1. Okay. I do not say that P1, P2, P3 are probabilities.
Okay.
Well, and you may ask, okay, so how long should we wait before the jump? You have to count, and the answer is the following. You have to count the local time, and when the local time at 0 is equal to some exponential random variable, then this is a moment of jump. And intensity of this exponential random variable parameter of this exponential variable depends on P2 and P4. And if P4 is infinite measure, then you also have some jump type exit from zero. But these exits, they looks like jumps of a subordinator with infinite measure Levy, with infinite measure Levy, and in some sense, the time of jump depends on the local time at zero. Feller and Wenzel, they considered this problem from the point of view of semigroups, resolvents, from analytic point of view. And it is, if you have just generator with a domain, it is not clear what is a probabilistic interpretation of this. I say that, okay, it looks like this, but it is not, it must be explained. And Ito and McKean, they constructed the corresponding process using excursion theory. Excursion theory of a Brownian motion. However, it would be nice just to have a function maybe of a Brownian motion and maybe of a subordinator with this measure Levy. We will discuss this a little bit later. And now let us, okay, we have already discussed Skorokhod reflection. Now I would like to discuss what does delay mean. So how to make a point sticky and for just any strong Markov process. And now this construction is quite standard. So assume that you have a strong Markov process, assume that, so real valued Markov process, and assume that a local time at zero exists, and let rho be positive number. So L of t is an additive functional. So let us consider this strictly increasing continuous additive functional. And this is just inverse function. And let us consider x at this point. So if the process x is not in zero, then L is not increasing. And if L is not increasing, then increments of A has derivative 1. So the flow of time just have a unit speed. Well, and inverse function also has unit speed. So you make some time transformation, and this time transformation, so the flow of time is has the unit speed if you are not at zero, but maybe you have some delay when you are at zero. And this process x rho spends positive time at zero. Well, you may do this construction, for example, for reflected Brownian motion, and then this process is called a sticky reflected Brownian motion. It spends positive time at zero, and moreover, it satisfies the following stochastic differential equation: dx of t is indicator x of t greater than 0 db of t. This is some Brownian motion.
Andrey,
Yes.
And why is a rho increasing, strictly increasing per function?
Because t is increasing and L is non-decreasing.
Yes, okay, thank you.
So plus dl rho of t, well, where L rho of t is equal to rho, I think, integral from 0 to t, indicator that x of s is 0 ds. By the way, oh, I forgot to mention, excuse me, that L, a function from the Skorokhod problem, is a local time, it appears, this is a result that L is a local time of x at 0.
Excuse me, but is this a local time for
not of a Wiener process, not of a Wiener process. This is
when we use arbitrary, when we consider deterministic problem. Can we say that this is a local time in some sense or not?
No.
So when we consider Markov process with good properties, then it is. Yeah.
Yes, then it is. Yes, yes, you're right. And it appears that this stochastic differential equation has only weak solution, not strong solution, not a strong solution. And this result was proved by Chitashvili, and there was another proof by Engelbert and Peschker, and it may be seen very strange that this problem has does not have a strong solution, but this process is a function of W, because L is a function, is a running minimum of W, A rho is a function of W, and this process is a function of W. And I write here B, some Brownian motion, not this Wiener process.
I'm sorry, Andrey.
Yes.
Did Skorokhod not explained intuitively that there is no strong solution himself?
I'm not sure. Maybe not. I'm not sure.
At least some hints about it may be found, I think, in his SD book with Gichman.
Okay.
Maybe non-rigorously. Maybe non-rigorously.
He constructed processes with delay, but I don't remember that he has some discussion about weak and strong solutions. Because his book in 1968, it was not so clear what is a weak solution and what is a strong solution.
Yeah, you're right. Okay.
And one more remark. So the pair X, which is constructed by Skorokhod formula, Skorokhod reflection map, and the pair just absolute value of Brownian motion and local time of a Brownian motion, it appears that this pair has the same distribution as this pair. But notice that this process L is a continuous function of W. But the local time of a Brownian motion as 0 is not a continuous function of W. If you construct some limit theorem using reflection map, then it's natural to expect that you'll have continuity principle, but not if you take this, because usually the local time of Markov process is not a continuous function of the trajectory. So we discussed delay, and now let us discuss. Now let us discuss jump exit from zero. And now let us consider the following generalization of a Skorokhod problem. So assume that you have two functions, x, a noise, and a function f. And I'll assume that f is strictly increasing. So in future, x will be a Brownian motion, for example, a Brownian motion, and f will be increasing subordinator. Assume that x of 0 is non-negative, f of 0 is 0, f of infinity is infinity. And I'm going to find a pair y and L of two functions such that y is a sum of a noise plus some compensation. And L is just inner time of compensation. And this inner time may increase only when the process y hits 0, and L does not increase when you are above 0. So if f of x is x, just identity function, then you just have Skorokhod reflection. But this function f may have jumps like a subordinator. And so this problem was formulated by me in 2011. And I proved that, I considered only continuous f, but it can be easily, the result can be easily generalized for x without, if x has no negative jumps. And it can be proved that this system has a unique solution, and there is a formula. So L is this function. So y has the following form, and now function f may be discontinuous, and this is not just inverse function, but so-called generalized inverse, and this function is given by this formula. I would like to mention that if f is continuous and strictly increasing, then f to the -1 is just regular inverse function, and this composition is just identity. So if f is continuous function, then there is no problem at all, and solution will be just classical Skorokhod reflection. However, if f has jumps, then you may have jump exit from 0. I also would like to note that this formula appeared in Blumenthal's book. Markov processes. Excursion of Markov processes. So I will give a reference after the talk, and he considered x a Brownian motion, and he considered f just a subordinator, and he said, okay, let us consider the following process. And then he made some sort of delay, and he proved this process is a strong Markov process that behaves like a Brownian motion above and has some boundary conditions like Feller-Wenzel boundary condition. Moreover, every extension of Brownian motion, okay, every strong Markov process that behaves like a Brownian motion should have this form, well, with some delay. And now I would like to formulate deterministic problem and then a limit theorem. And at first, let us consider some auxiliary so-called switch problem. The blue function is so the blue function is a noise, and red function I will call regulator. And delta is just a positive number, just a positive number. Assume that, and let me start with interpretation. Assume that you are the owner of internet shop and you have a storage. And the noise is, so you sell some items and you refill your storage. So some items arrive and some items depart. So people order, but you also have some regular order. Okay, and you sell, you buy, and sometimes people order more than you have. Well, when you have a regular shop, when a customer come and say, okay, I would like to buy this, and if you don't have item, then okay, you have just zero. You have zero. But if you are owner of the internet shop, you may say, okay, no problem, just pay me money. And customer pay money, and actually you don't have items. So the number of items at the storage is negative. Is negative. So what are you doing then? Then you say, okay, I must buy these additional items. And you say, okay, please sell me to other storages. Please sell me a few, say, kilograms of sugar or few t-shirts. And usually, well, there is no sense to buy just 2 kilograms or just 2 t-shirts. And people answer, okay, you may have just a truck of sugar or say 1,000 of t-shirts. So blue line is the number of goods, and then this red mean critical regime. So when you buy items in a hurry, so you buy, and you have, okay, zero, and then, okay, thanks. And then you continue this function, and then again, and this jump means that you buy just a truck, and then you continue, and so on and so forth. So when blue part of the trajectory is below minus delta, or just hit minus delta, you switch to this critical regime, critical mode. And when the process is positive, non-negative, you just switch to regular mode, and so on and so forth. Or another interpretation. Well, in the future, I will consider this random process and this random process. And well, it will be just regular mode and critical. For example, a student, and this is amount of money that he has, or just celebrity or YouTube blogger. And well, a person can buy something in a credit and have some negative amount of money. And that what a student does when he has, or YouTube blogger, when he has a negative number of money and less than some critical level. He says, parents or just subscribers, just help me, please, if you want to have my tweets. And this is critical, so this is critical mode when parents or subscribers give some money, maybe buy a big jump. And when amount of money is positive, then blogger says, okay, thanks a lot for this, and especially for a person who give this big jump. And then the process continues. Now, I would like to formulate the following theorem. Assume that you have a sequence of Cadillac functions that converge to a function without negative jumps. And these regulator functions converges to increasing function, maybe discontinuous. And that this delta converges to zero. Delta converges to zero. And my aim is to prove deterministic theorem, and then to apply to stochastic processes. I will write this output as a function, say S, that depends on delta, X, and F. And actually, this regulator may be non-increasing. So it is possible that the regulator is this. So you have the picture like this here. And now let me formulate the main theorem. Assume that there are two sequences of functions, and noises xn converges to some function x0, fn converges to f0. This limit regulator is strictly increasing, and x0 does not have negative jumps. And assume that yn, oh, it should be s, sorry, is a function of xn, this noise, this delta n, and delta n converges to zero, and these regulators, but these regulators, so we change the flow of time. So we speed up or just make effect of fn slower. And let us assume that this number rho n converge to rho in 0, infinity, and 0 and infinity are possible. Then you have convergence of yns, and what is their limit? Their limit is the following. You have to consider reflection, jump type reflection problem that we discussed, and to slow it down, So let me recall that this function was L of t. This function was L of t. And this is the inverse function. Few remarks. If x0 does not have negative jumps, then this m0, so m0 is a running minimum of m0 of t is the minus, so this is infimum s in 0t of x of s minus. This is running minimum. It's continuous, and f0 is strictly increasing, so its generalized inverse is continuous function. So L of t is a continuous function, and this is strictly increasing function, and this function is just inverse, regular inverse. Well, if rho is 0, then you have a solution to jump, then y0 is just a solution to jump exit process from 0, where regulator is f0. And if rho is infinite, so this means like infinite delay, then the process is this. Okay, it's just x0 t minus sigma. So the process hits 0 and leaves, and then stay at 0 forever. Well, formally, if rho is 0, then you don't have this, and you will have a rho is t, and you may also write here a rho minus first t. And if rho is infinity, then also just formally, then this function is like this: t before you hit 0, and then infinity after. And this function will converge to x0 just stopped at 0 if rho in this formula converges to infinity. So in all three cases, the result is this: rho infinity means just stopping at 0, and rho 0 means like instantaneous exit from, instantaneous in some sense, exit from 0. Let me consider few examples. And the first example is just Brownian motion. Assume that the noise is, well, excuse me, I forget to say that one important thing, that if you have this theorem, and if xn and fn are stochastic processes such that yn satisfies this, and if the limit process does not have negative jumps, and if f0 is strictly increasing, and okay, I didn't discuss this. So this is a price for this theorem. Then you will have weak convergence of yn to this process. For example, if xn and fn are just random walks that converges to subordinator and or to Brownian motion, then this will be, so these four conditions are easy to check. And the only non-trivial assumption is this. So what does it mean? You have function f, which is strictly increasing and may have jumps. And you have running minimum. Okay, so so it is non-decreasing process, but sometimes it may be equal to a constant. So do not increase. So this assumption means the following. So if this is a point of a jump, then you can't, then this process cannot have interval of constancy at the same level. So this picture is bad. So if you prohibit this, then you have convergence. And well, if f is increasing subordinator, and if x0 is Levy process without negative jumps, and if x0 is independent of f0, then this condition is satisfied always.
By the way, let me ask you about this independency. You did not say anything about mutual distribution of x and fn.
I say that this is deterministic theory. If
yes, but after this you begin to say about
I say that
the application when xn and fn.
If you apply this theorem for stochastic processes, and if in a limit for some delta x, if this limit process x0 is Levy without negative jumps, and this is increasing subordinator, and if they are independent.
Oh, so you did not mention this. You did not mention independency.
No. So okay. If you have independence, then you have convergence.
Yeah.
Okay. But this may be dependent. Okay.
Yes, I understand a purely deterministic statement, but in general case, you need some assumption, I think, about the behavior of the pair of xn and fn, because in opposite case you can have different limits or something.
No. The statement is if a pair converges, well, if you're right. If a pair convergence, yes, you're right. If a pair converges, and the limit x0 and f0 are independent, then you have this.
Okay, thank you.
However,
so the pair converges not independently n and f.
Yes. Okay. I have to think about this, but it seems to me that if every coordinate, no, pair must be convergent. Okay. Yes. And now let us consider a few examples. The first one is just assume that the noise is a Brownian motion, and assume that regulator is just constant function, is a linear function with positive a. So this is level minus delta n that converges to 0, and you have a Brownian motion before you hit 0, then process behaves as linear function, then again Brownian motion before you hit 0, then again linear function, and so on and so forth. And now let us send delta n to 0, then what will be a limit? Then the limit will be just sticky reflected Brownian motion, because the inverse function, okay, it's just easy to calculate function f, its inverse this, and you will see that it is just sticky reflected Brownian motion. And if the regulator is not AT but ANT, where AN converges to infinity, then the limit will be just reflected Brownian motion, just ordinary reflected Brownian motion without any delay. And delta n's and ANs are just any sequences. Well, delta n must converge to 0, and AN converges to infinity. Another example. Consider so-called storage process or DEM process. So, for example, what does DEM model means? You have a lake, and you have water in a lake, and water is evaporating with intensity Rn. But sometimes, no, excuse me, sometimes there are rains and you have jump up and so on and so forth. Well, if you hit 0, then you stay at 0 some exponential time, and then you may exit by jump and so on and so forth. These psi k, well, n are independent identical distributed random variables. This is a Poisson processes, and we assume that everything is independent. Everything is independent, and well, jumps from 0 may have different distribution than jumps here. Oh, excuse me, I forget to say the following important thing. When I formulated this switch problem, I need to have positive delta. I cannot take delta 0, because if you hit 0 and regulator goes down and compensator goes up, you don't know which mode to select. But if there is no contradiction, then you may consider the following result for delta, if delta is 0, 2. For example, if x and f are just piecewise constant functions, then there is no problem. Then there is no problem. And if you consider, so let's consider this DEM process and some assumptions. For example, assume that you have this, and this, then the first process converges to a Brownian motion with a drift. And this is a Poisson sum of non-negative random variables. So assume that for some gammas, you have convergence of these to t. For example, if zeta k are independent of n and have identity, so if their expectation is 1, for example, or alpha, then this gamma n is 1 over alpha, is n over alpha. Or if you take this zeta like ckn, then this gamma n is, let me think, what is this? It should be something like 1 over expectation of this. No, it's xi kn. It seems to me something like this. And conditions of my theorems are satisfied. If so lambda n is intensity of this Poisson process. If you have this, then the limit of this DEM process is just sticky reflection of this, sticky Skorokhod reflection of this, and this results for zeta is xi was obtained by Harrison and Lehman. But my deterministic result is universal. So you may have take any zeta k, and you may assume that the limit of this may be not t, but maybe just subordinator, and you will get jump type reflection, maybe with a delay of this diffusion. And the last example is the following. Perturbed random walks. Assume that xi is the following. So you have just a random walk, and this random walk under Donsker scaling converges to a Brownian motion. You have this random walk if you are above 0, but when you jump below 0, then you start another mode, and another mode is the following. You start to add independent random variables with distribution eta before you enter positive half line. And let us assume that eta belongs to the domain of attraction of positive alpha stable law with alpha here. And the question is, what is the limit of x, of Donsker scaling of x? And please notice that scaling for eta and scaling for natural scaling for eta is, n to the power 1 over alpha times some regular slowly varying function. So it's different. It is different than Donsker scaling for xi. And it can be seen that the random walk y is this switch problem. Okay, let me write G0 of random walk S xi and random walk S eta. So S xi is just sum of xi's, S eta is sum of etas. And if you consider Donsker scaling, then you have to introduce Donsker scaling here and there. But Donsker scaling, be careful, is not natural for S eta. But it may be seen that, oh, it is X, our perturbed random walk, that this scaling of X is switch problem for two functions. The first one is this, and the second function is this, and I multiply by rho n and divide by rho n. So this is analog of that rho n. And I select rho n such that rho n times n, rho n times n is such that this sequence converges to alpha stable subordinator. And alpha is between 0 and 1. Hence, this rho n converges. So this Bn is slowly varying sequence with index alpha over 2, and this rho n converges to 0. So this means then in a limit, you have, I call this just instantaneous jump time type reflection at 0. And the limit process is this, and U alpha is alpha stable subordinator, and M is a running minimum of a Brownian motion. And this result was obtained in a joint work with Yura Prihodko and with Alexander Iksanov and Ben Power. And we also considered some other perturbations, some other time. We consider this and some other perturbed random walk, but the limit was this. And it was not clear how to get the problem is so it was not clear for me why different scalings for eta and psi, how they interplay, and why norming for sequence of etas disappear in a limit. And now we see that, well, if you formally introduce this delay or or speeding the type, that you may obtain this result of a general invariance principle. And I have not time at all. Sorry that my talk was more than 1 hour. Just one remark how to guess the answer for a time. Solution of this switch problem can be written as follows: effect of x, so but the t of a is time spent in usual mode, and plus f, this regulator, in its own time, and some of these times is t. It can be seen from the picture or from some reasoning that we always have this inequality and this inequality. And if you have sequence of delta n's and xn's and fn's, well, by the way, TA and TB, they're Lipschitz function, and Lipschitz constant is less than 1. So sequence of TAN, these flows of time in first mode and in alternative mode, are how to say, relatively compact. And if we select a convergent subsequence, so let us select convergent subsequence, and then we pass to a limit everywhere here, then what will we get? this will convert to 0 because the limit process does not have negative jumps. This sequence will not have, is 0. The limit of this is 0 because f0 is strictly increasing. Delta n is 0. And so we have this. So limit of this fn, well, let me write it just formally. T b0 of t is greater than this and is greater than this. So just take generalized inverse of this, and it can be seen that tb0 of t, so limit of tbn, is equal to this generalized inverse of this, of this. So this is just a guess. And sum of this and this is t. So this is equal to t minus ta0 of t. And if you move this function to the right hand side, then you see that t is equal to, oh, and I forget about rho, so let me write rho here. Then you have this, t is equal to, this is just formal calculation, to this. So what is ta? Ta is the inverse function to the following, and I denoted this function by a. So ta of t should be the inverse a minus first, oh, okay, L, where a rho of t is t plus rho L of t. So we have t is equal to ta plus rho L of ta. So ta is just inverse. Certainly, when we have equality here, and if you prove convergence of tan to some function, then you have to prove convergence of compositions, of this composition and of this composition, and convergence of sum of two convergent functions. And here, a condition about jumps of running minimum, the condition, this condition is very, very important. Without this condition, the result is not true. And that's all for today. Thank you for your attention. Just let me show you a few results, Feller and Wenzel about the boundary conditions, and result of Ita and Makin about probabilistic construction of diffusion. These are papers by Skorokhod when he introduced reflection and processes with reflection. The next result devoted to study of sticky reflected Brownian motion. So this result by Engelbert and Pesker on equation, stochastic equation, and these results are on a limit for storage processes where delay reflected diffusion appeared. These results are about stochastic differential equations with jumps from the boundary. Mikhailovich considered martingale problem approach, and Anulova considered just classical equations. And this is a result by Watanabe, who constructed diffusions with Wenzel boundary conditions using so-called Ito excursion theory. And this is a book by Blumenthal, and my paper on jump-like exit from zero, and our results about perturbed random walks with reflection. Okay, that's all. Thanks. Thank you for your attention.
Thank you very much. And maybe somebody have questions or comments, please.
Maybe small question. I know that there are some works of Martin Grothaus about sticky reflected Brownian motion. So is there known?
Who?
Martin Grothaus.
So I will check. Thank you.
Probably I will send some more detailed information.
Yeah. Well, there are papers on reflected. So this is the not full list.
Yes, of course, but this was sticky reflected. Sticky reflected.
Yeah. Yes, I understand. Thanks.
Okay.
Some other questions, please. I have a question relative to this deterministic construction. How do you think, can it help to understand the necessary enlargement for filtration when we discuss that absolute value of Brownian motion is just weak solution of those stochastic differential equation with the local time?
I would say no, it will not help, because it is because as you see, my processes are f functions, so are a function of a regulator and a noise.
Yes.
And
yes.
for example, so let me make a picture once more. So assume that you have a reflected Brownian motion. Say, just take absolute value of a Brownian motion. And then you make this transformation of time, t plus rho L of t. Or if this is Skorokhod reflection, then what do? Then you have some parallel just move of this. So for example, this part will be somewhere here, this part will be there, so this is something here. You stretch the time only when the process is at zero, and the structure of this set is very strange. It is nowhere dense set, and after stretching, this will be nowhere dense set of positive Lebesgue measure. And you see that okay, behavior here, so increments here are increments of a Brownian motion. But when you write equation dx rho of t for this sticky delay is indicator x rho is positive dw of t, this Brownian motion for this blue, for this sticky reflected is not this one. It's not this one. It's not this one. And well, plus some reflection. And this x row is not a function of this W as Chitashvili or Engelbert and Peshker showed. However, in my case, when I write just x is a function of a row minus 1, and you have a Brownian motion, and its running minimum, then this process is a function of this original noise. So I cannot see any idea how to get
Actually, this was a reason that
this is a miracle.
pair,
Let me say.
no, you said, and it is known that the pair WL is equidistributed with the pair absolute value of W and local time, yeah?
Mhm.
And but you construct this W and L using Skorokhod reflection, yeah?
No,
So,
I have W. I have W.
Yes, yes. Maybe if we follow carefully to this construction, we will understand what we lose in the information when just have this reflected process, and then we can came back.
So you see here we lose nothing. We lose nothing at all.
Mhm.
So when we have Skorokhod construction, x of t is W plus L of t, then filtration generated by x is equal to filtration generated by W.
Mhm.
So if you have x, then you can recover W.
Yes.
But filtration
Of W. This is you know.
but
I am keeping
filtration
in
of
mind
this
just
is not
yes,
equal
it's
to
small.
filtration of this.
Exactly. So I was keeping in mind the just more easy case of Tanaka equation. In those case, we can say that clearly the we lose only the sign of excursions. That's all. And
Yes.
that we have to find the Bernoulli sequence, and that's all what we need to add. Maybe in this case, I remember that we with Engelbert discussed this this idea how to recover the necessary sigma field related to this weak solution. And he said that he wanted to do something, but unfortunately he passed away. Okay, thank you very much for an interesting talk related to different subject of random process theory. As far as I remember, our next speaker maybe is Georgi.
Yes.
Yes, okay. Don't forget to make announcement about your talk.
I will not.
Okay. For today that's all, and see you next week. Bye, everybody.
Thank you. Bye. Thanks for
Bye.
the talk.
Goodbye. Thank
And
you.
fun examples.
Bye.
Yeah,
Bye.
bye-bye.
Goodbye.